All right, I think we're ready. Last time we introduced the course, the statics and strength of materials course, and we mostly did statics. And today we're mostly going to do, actually, I think we're only going to do static stuff today. And then Wednesday we'll start on adding in some of this strength of materials type things. So you can kind of see the schedule here. We did 2D concurrent force systems last time, plus intro to just things like resultants and force components, and so your basic review things. So last lecture on June 3rd should have been all review. Today should be maybe about like half review and half new stuff. Gonna add in the 3D idea. So last time we had our little weight with two cables holding it up, something like that. This time we'll add in a third cable. It's gonna be hard for me to hold three cables at once, but something like this. They won't all be in the same plane. They'll be out of planes. We won't necessarily do this one. I've got a picture that we'll work on, but something like this where there are three forces. Still they are concurrent though, so it will be forces that their lines of action all intersect at a single point. So we'll still keep that part of it, and but we won't have anything like moments that we have to deal with because all the lines of actions are going to intersect at a single point. So what I thought we'd do is we would start with kind of reviewing the 2D by working a problem. The problems I'm grabbing are from the optional assignments. These OP, I didn't really explain this part last time. I don't think I did anyway, because I had some questions about it. So for your homework, the HW 1, 2, 3 all the way through, I don't even know how many, 20 something, 20, maybe it's 20. Those are the homework assignments, the ones that you need to finish and complete. Then there are these CH 01 and 2 and 3. Those are challenging problems. CH1 are challenging problems for exam 1, and 2 is for exam 2, and 3 is for exam 3. There are not as many of those. Let's see. Oh, I gotta log in. 6 of those in the challenging set. What these do is, first of all, they're harder. They're more difficult problems to solve. But if you do solve some of those, then they will add into your homework grade. So say you missed problem 2 on homework 1, but you finished part of one of the challenging sets. Those challenging sets will fill in, and if you've done all of your homework, web work, homework, then they add on top, so you can actually get a little bit of extra credit into those homework assignments. The OP, those are optional. These are pretty much book problems that have been randomized and created in web work. They don't give you any extra credit, but they are not as hard. They're not as challenging. So they are good for practicing, like for the exam. And there's a lot more of those. Let's see how many of these there are. There's 38 of those in set 1. You don't get extra credit for finishing the optional ones, but you get extra practice for finishing the optional ones. So I thought I'd point that out. So what I'm going to do is actually I'm going to take some of these optional ones. I'm going to take number 2. So I'm going to take this one and work it. I'm going to take it for a couple of reasons. It's a 2D problem, so this is not 3D. But it has this new element here, this collar, this slide. I built it in SolidWorks here. And so you can kind of see what this is doing. You need to be able to understand the fixtures and the elements so that you know how to draw their reactions. So this little gold part or brass part, that's the collar in this picture. So that's this little guy. I didn't really draw it to scale, at least not to the picture. And the rod here is the rod that it's sliding on. And so when you have one of these collars, in this course, we're almost always going to assume there's no friction involved. Friction between this collar and the rod that it's riding on. Unless there's a problem statement that specifically gives you a coefficient of friction for this course, then we're going to assume that it's 0. And I don't believe there's any instances where I can think of where you actually do have friction included in these problems. So what this does is it lets this collar move up and down, but it doesn't let it move, perpendicular to the shaft here, to the blue piece now. It only lets it move along that axis. So when it does that, it's sort of acting like a wheel rolling on the ground where there's no reaction in this direction. The collar's free to move this direction. The only reaction for this collar is perpendicular to the axis of the rod. So it'd kind of go off in this direction. So I'm going to close this down so we can, we'll save those. Rebuild and save, that's fine. All right, so this is the problem we're solving. We've got a couple of angles, alpha, beta. We have this cable that, remember, cables, ropes, chains, they can only support tensile loads as far as we're concerned. It would take a really large diameter cable to support some kind of compressive load. And we're assuming that's not what we're dealing with. We also ignore their weight. We assume that their weight is really small compared to the forces that they're dealing with. So we ignore their weight. Whereas, an actual cable could have enough weight that you have to consider how heavy this thing is. But here we're going to assume that this only carries tension and it doesn't have an important weight, so we don't have to worry how much this little cable weighs. This collar is frictionless. This one doesn't actually say that. The problem statement doesn't say anything about it being frictionless. But we're going to assume that since it doesn't say anything about it having a friction coefficient either. And so the reaction at this collar is going to go perpendicular to BAC. So we're going to have it going off this way. It doesn't matter if you draw it going up and to the left or down and to the right, just so long as you put it in that line of action. So I've already copied this over to here, I think. No, not to there, that's Mathcad. To here. Let's see. And what we're going to do with this is we're going to, first of all, we don't have a free body diagram here. This is just a sketch or maybe just a diagram. So we need to convert this into a free body diagram. So what I'm going to do is I'm going to redraw it. I thought about drawing on top of this. I don't think that's the best idea. I'm going to take the body of interest as the collar. So the little collar here, that's going to be the thing we're interested in. That's the free body that we're going to isolate. So let's just go over to the side here. Make sure I'm still on the screen. Kind of draw the body. It doesn't have to be super accurate as to representing the body that we're copying. It could just be a dot. So a lot of times for a concurrent force system, you just draw the body as just a dot, the center of the body. I'll draw something that kind of looks like our collar. We obviously have force F. I'm also going to put kind of the center of this thing, just so we have that. Force F for me is 975 pounds. And then we have cable AD. I don't know anything about its force. I know its angle is alpha, and it tells me that the problem statement tells me that alpha is 19 degrees from below the x-axis. And I also know it's a cable, and that cables only support tensile loads as far as I'm concerned. So I'm going to draw a tensile load by drawing an arrow away from the body. So like this. And I'm going to label it, I don't know, so I'm just going to call it the TC, tension in the cable. Call it that. And I can remember from our SolidWorks picture that the reaction for the collar, it's trying to move in this angle direction, angle beta, along BAC, the rod. And it can move that direction, but it can't move perpendicular to that. So if it can't move perpendicular to that, that's the direction that something is holding it from doing. So I want to draw it this way. you could just as easily take this same arrow and draw it this way. You know, we could do either one of those arrows. There we go. Let's just label it F. We could do R or whatever. It doesn't really matter. Let's put our coordinate system in here. So I'm going to use an x-axis and a y-axis. I could, in this one, elect to choose the x-axis as the same axis as BAC. You know, I could do that. But all my angles, alpha and beta, are measured from what they've drawn as the x-axis on their diagram, so I'm going to keep that. So alpha for me is 19 degrees here. Beta, now this one is actually giving me the angle of the rod. And it says the angle of the rod is 29 degrees, so I should have drawn it a little bit more, less steep, I guess, a little more shallow, but that's fine. So in this case, the angle or the force, the angle of the force F is perpendicular to this line. So an easy way to establish perpendicular is if the dotted line represents the shaft BAC and it's 29 degrees from horizontal, the x-axis, then perpendicular to that is 29 degrees from the vertical axis. So right here. Remember, there's 90 degrees between two perpendicular lines, so I just basically add 90 degrees, or I measure from the y-axis if I measured the other one from the x-axis. Oops, wanted to keep that there. All right, so that's my little free body diagram. In fact, I'm going to simplify it by erasing some of this because it's going to get in our way, I think. All right, we'll leave that in there just because it's hard to erase. All right, so let's take this guy and move him somewhere down here. Oops. Oh yeah, that's in our way. We'll get to that in a minute. In fact, let's see if we can move this down. That's for the 3D stuff. We don't need that yet. All right, back to here. So now I've got my free body diagram of my 2D concurrent force system. And I know that I have two equations, since this is in equilibrium. I don't know if the problem stated that. It does not. But you kind of assume that this is in equilibrium, static equilibrium. If it doesn't specifically say it, and we're in a class called statics, then we can assume that this is supposed to be in static equilibrium. So that means that if I draw the free body diagram of any part of this system, that if I add all of the x components together, they have to add to 0, or else the body I've drawn is moving in the x direction. And same thing for y. Let's write our x equation first, and then we'll write the y one. So the way I've drawn it, and I could have drawn, I'm pretty sure I drew the TC arrow the right way because it's a cable in tension. And if I think about this, I'm pretty sure I've drawn the F correctly. But don't worry too much if you don't know which way to draw the arrows. All that'll happen if you draw them backwards from what they should be is you'll get a negative number telling you that, oh, you should have drawn that arrow the other direction. That's all that'll happen. So in the x direction, I've got TC times the cosine of 19 degrees minus F times the sine of 29 degrees. And those have to add to 0, or else the free body is moving in the x direction. And then I have the same equation in the y direction telling me that if all the y components don't add to 0, then the free body is moving in the y direction. So that equation would say, now here I'm going to do a particular thing. Notice the order I wrote these in. I wrote TC first and then F, which didn't at all matter in the first equation. But now, since I want to solve this a particular way, I need to write TC as the first variable in the y equation. So TC has a negative y component. It's pointing downwards a little bit. So minus TC times sine 19 degrees. F has a positive y component. It's pointing mostly upwards. Plus F times cosine 29 degrees. Remember, if you sines and cosines, you have to remember the definition that cosine is going to give you the component that's adjacent to the angle, and sine is going to give you the component that is opposite the angle. So don't, unless you've chosen to do all your things measuring from the x-axis, don't automatically assume cosine is going to give you x components. It just gives you the component that's adjacent to the angle that you're using. Now this one I can't forget, the 975 pounds. That I'm going to do a different type of thing. Actually, no, I'm going to leave it this way. Minus 975 pounds equals 0. But now I'm going to take, because of the way I'm going to solve this equation, I'm going to take the 975 and move it to the other side of this equal sign. So my equation will actually look like this. And that 975 becomes positive. Like that. Now I think I'm going to copy these two equations because I want to do a particular thing with them. Let's paste it over here. And then let's take this one, the one with the 975 on the right hand side. Actually, let's just move it. Oh, keep hitting the wrong buttons. There we go. And I want to line those up. So why I'm doing this is because I'm going to use a particular method to solve these simultaneous equations. Now there are only two here, so I probably could just use substitution or just add the equations together, something pretty straightforward. But I want to start setting up a way that's going to help us solve, if there's more than two equations to solve. So a couple of things. First of all, I've got all the TC variables lined up in a column, and I've got the F variables lined up in a column. So my variables are aligned in these columns. And then I need another highlighter. Here we go. The numbers that aren't associated with variables, so these constants over here, I've got them all isolated on the other side of the equal sign. So what I can do with this setup is I can create a matrix here and create a matrix here, and the matrix is going to look like the coefficients here. So cosine, let's do this, cosine 19 degrees. I have to keep this negative sign, so negative sine 29 degrees, sine of 19 degrees, cosine of 29 degrees. So that's the coefficient matrix for TC and F. Right? So if I took those matrices together, I could recreate the one that I just wrote with all the colors in it. Equals this matrix full of constants or residuals. 0 pounds here. There were no external forces in the x direction. 975 pounds here. There was the 975 pound external force in the y direction. Now it does show up as positive in my diagram that I drew. It looks like it's a negative y, but remember that it's positive because of this equation up here, how it became positive. Now what I can do is I can do a little bit of matrix math here, and if I take and divide this matrix. So if I divide through by this matrix, so in other words, if I do, in order to divide it, I could, raise it to the -1 power. And then I would have this. Whoops, get off of there. So I'm dividing it through, moving it to the other side. Oh, well, hold on, I didn't move it yet. Times. I don't need that underline. Equals the TC and the F. So all I did is divide the coefficient matrix, divide both sides by the coefficient matrix. And so on the left-hand side, it actually becomes just 1 times TC over F, or TCF matrix. And when I solve this, I'll get values for TC and F. So let's go to Mathcad, write this equation in, just like, well, pretty much just like it looks here, and see what TC and F should equal. So here we are in Mathcad. This is Mathcad Prime 5, so there's a newer version out. Maybe you're up to 6 or 7 by now, I don't know. Control M is create a matrix. Our first value in this matrix was cosine of 19 degrees. So we'll just write cosine of 19. Now we do have to specify that it's degrees because Mathcad is going to assume that it's radians otherwise. Shift space to add, what's the next one? Negative sine of 29 degrees. So we just put negative sine 29 degrees. We need another row, which we could tab, I think. Yeah. And this one should be sine of 19 degrees. And this one should be positive cosine of 29 degrees. Okay. This whole thing we want to raise to the -1 power. Whoops, I did the wrong thing. -1. And then we want to multiply this whole thing times a new matrix, which is the residuals, the constants, 0 pounds and 975 pounds. And then hit equals, and let's make it in pounds. And 479 or 480 pounds, 936 pounds. I don't actually know the right answers. Let's see. Let's check our correct answers. Oh wait, they have different numbers there. They have 1377 and 706. I might have typed something in wrong, which is entirely possible. I think 29 degrees, 19 degrees. Let me check the numbers here, because we should have gotten the same numbers. Actually, I'd never checked that this problem was calculating correctly anyway. Force from the rod should be what we have as F. And force from the cable is what we should have as TC. And we've got 470. Yeah, we don't have the same number. Well, I'd have to dig into this to see if there's a problem with the web work problem or if there's a problem with what I wrote down. Let's just briefly check and make sure we drew everything correct here. So it was 29 degrees from horizontal, and it was 19 degrees below there. We wrote x was cosine of 19. Is the sine of 19 degrees also negative? Oh, yeah, I think I didn't. Yeah, it's right here. Negative 19, and I wrote it there, but somehow I lost it there. Good eye. Let's fix that. And there's the numbers that they're expecting, the actual answers they're expecting. So good time to mention the problem with these is, you know, these little tiny details. We left out this one little, we brought it all the way down to here, but then right here we lost it. We lost it here too. And then obviously we didn't put it in Mathcad where it actually mattered for the calculation. So we lost that negative sign, which caused our whole process to fall apart. So that is a downfall for simultaneous equations, is we got numbers and they were kind of realistic numbers. You know, they weren't crazy numbers. And so you have to be very careful when you're solving simultaneous equations with some sort of, you know, calculator, Mathcad, or whatever it is. In this case, we forgot this little negative sign, got kind of realistic numbers, but then, and there was no, you know, all of this is right. We did right here, but we just dropped it off right there and right there. So you have to be very careful with this. We probably wouldn't have had that issue if we had just tried to solve these two with, you know, substitution or something like that, because you're just dealing directly with the equations. Except the issue is when we get into, you know, 3 unknowns, which will happen in 3D concurrent force systems, that substitution gets a lot more difficult to do. All right, so thank you all for finding the negative sign missing, because that solved our little problem. Why I showed you this method is not so that you can do it in Mathcad. Mathcad actually has a simultaneous equation solver where we could just put the equations in and tell it to solve them simultaneously. So we could have done that. Why I did it this way with the matrices is because pretty much every calculator you're going to use for an engineering exam can at least do it this way. Some of them have built-in equation solvers, simultaneous equation solvers, and some don't. Some of them you have to use this type of method where you build the matrices and invert the coefficient matrix, multiply times the residual matrix, and out comes your variables answer. So I'm showing you this way because I know that pretty much any calculator you're going to use engineering is going to at least be able to do this. A lot of them have their own simultaneous equation editors, which basically they take these equations and follow the same rules. So you have to have all of the, in most of these simultaneous equation editors on calculators, you usually still have to have your variables lined up, all of the TC variables in the first column, all the F variables in the second column, all the Y variables or whatever they might be in the third column. Most of them still work that way. Basically, a lot of them have you build this matrix as how you input the equation into the solver. So that's why we're going to do this one. But they are susceptible to those little tiny errors that are easy to not see. All right, so that's 2D. That's a little review of what we've been doing last time. Let's go to 3D. So I've got this isometric dot paper in an attempt to help us draw our 3D vectors on a flat piece of paper or a flat screen that you're looking at. And so isometric dot paper, and there's isometric grid paper also. I like the dots because it's not quite as busy with all the lines everywhere, but whatever you like is fine with me. So how this works, if you notice, the dots aren't necessarily all aligned in a grid. They are in columns. You can see columns, and then there's 2 sets of rows kind of interlaced with one another, and they're offset. So what this does is, like if you wanted to draw a cube on this kind of paper, let me get it where I can see the paper. You would draw in, you know, a lot of times you'll use the, let me look at a problem here. Well, where'd it go? It's on my other screen. Well, do I have a good one to look at? I guess that's good enough. So a lot of times we'll have, let's draw an XYZ axis. So let's draw the X along these lines. We'll draw Y out here. And then Z is going to be our vertical axis. Now this might look like an odd configuration. Normally you're used to X being horizontal, Y being vertical. So why did I make X be coming towards you? This is following the right hand rule, where you actually take your right hand, so your right hand, and you take your fingers and curl them from the x-axis to the y-axis in the direction, like on our screen, X is kind of this way and Y curls around, you know, I'm having to do it backwards from me, curls around this way. And what that does is it makes the thumb point upwards. The direction that the thumb points is your positive Z direction. So if I had them the other way, where X was kind of going this way, going out this way, so you would curl from X to Y, it makes your thumb point down. And that, if I had drawn them that way with X towards the back, then the positive Z would actually be going, you know, downwards, which is not really what I wanted. So that's the reason for this arrangement of X, Y, and Z, is so that I have a positive Z going up, which makes X go kind of towards your left. And then if you curl your fingers from the X-axis to the Y-axis, the only way your hand can do that is if the thumb is pointing upwards, and the thumb direction is the Z, positive Z direction. That's called the right-hand rule. So you can kind of start to see with these axes on here how the coordinate system can fit into these dots. So if we wanted to draw a cube, we could maybe draw a base of 3 in both directions, X and Y. So there's its base, and then a height of 3, 1, 2, 3, and there's its top. And there is your cube. You know, you've got a face over here, kind of facing to your right. There's a face over here, kind of facing to your left. And then the top on that I didn't shade in. I guess I could do this color. The top up here. So there's no perspective in this isometric dot paper, so it's not going to show things that taper off into the distance. Everything's going to be true scale, you know, in every direction. So the things you draw, well, if you were to draw like a cube, it's going to look a little bit odd. It'll look 3D, but it won't look, you know, real, because there's no foreshortening and no vanishing point or anything like that. But it's useful as a way to kind of visualize where the different forces are acting when we're trying to draw a force system here. So let's draw another coordinate system so I can show you how I'm going to put a force in here. So here's our X, Y, and Z. So usually, again, we're doing 3D concurrent force systems, so the origin is going to be that point where all of the lines of actions intersect. So I want to start our force right here, and then I'm just going to pick a direction to draw it. Let's draw it like that. Now, you kind of have an idea where that force is going, but some people might look at that and it looks like it's in the YZ plane, kind of pointing up and to the right. Other people might look at it and interpret it as in the XY plane, pointing backwards. And it could be neither of those. So how we're going to try and show this is, there's two ways. One way is we will show going back 1, 2, 3, 4. So that's a -4 for the X. going over 1 in the positive y, and then going up 1, 2, 3, 4 in the z direction. Oh, I lost my, there we go. There we go. So I went from there to there to there. So you can get the sense now that it is pointing back, but it's not laying down in the XY plane. It's actually in none of the coordinate planes. It's closest to being in the XZ plane, but it is shifted over just that one, that one little unit there. The other way we might show these is not with the lines, but with just its coordinates. So x of -4, y of 1, z of 4. The coordinates from its origin to the endpoint of the vector. So those are the two main ways that we'll show how these forces are situated in 3D space. There might be some variations where instead of these blue lines, it's just dimensions that show, but they'll be representing basically the same thing these blue lines are representing. So let's see. Let's actually copy our page of grid paper and paste it back so we have a blank one. And let's go back to our web work. Where did I put it? It's over here. All right, so let's grab a different problem. I'm going to grab problem 6. So 2, 3, 4, 5, 6. This one. All right. So let's solve this problem in 3D space. It has the same x, y, and z, but notice a couple of things. First of all, the origin of this coordinate system is not the place where all the lines of action intersect. All the lines of actions intersect over here at A. So when I draw this setup, I'm actually going to have the origin at A, not where this origin is shown. All right. Said we were disconnected, so I paused there for a second. I think we're back going. At least as best I can tell. Things seem to be moving again. All right, so what I was saying is that AC and AB are struts, so they're rods. So they could handle a compressive load or a tensile load, and we don't really know. We still are assuming that everything is an axial load. So the load, the force in member AD or AC or AB is axial, meaning that it's along the line of the member itself in this case. There's a little more to it, but for now that's fine. In other words, it's not flexing, it's not bending, and it's not twisting. It's either just stretching or compressing. But we don't know about AC and AB, so those could be tension or compression. And looking at this thing, if I imagine a force pulling down at A, then I kind of think AC and AB are actually in compression. They're trying to be squished a little bit. And AD, the cable, is clearly trying to be pulled. So I think AD is tension, AC and AB are compression. What that'll mean in our answers is the way I'm going to draw it, I'm going to draw all of the forces as tensile forces. And tension forces go away from the free body diagram. So I'm going to draw them that way. And if I was right that AC and AB are actually compressive forces, but I drew them as tensile forces, then I will get negative numbers for their values. Because I assumed one thing, tension, but they were actually the opposite of that, compression. So I assumed them to be one positive number. They're actually the opposite of that, and I get a negative number. So let's take this picture. Let's see how is best to do this. See if we can just copy it. Copy image. And let's just paste it, not in Mathcad. Let's paste it in here. Actually, let's move this guy down so we can paste it right above it, and then we'll work on it. Right. Oh, all right. There we go. Kind of overlapped. We'll make it a little smaller. All right. In fact, we could probably just put it on top of it. And that would probably give us more room. Actually, let's put it on this side. because all the stuff is going to be coming off to the right. All right, so this one might be easier to draw our coordinate system first and then put the forces on it. So I'm going to put our coordinate system, it's going to start 0, 0, 0 is going to be at A. So I'm going to pick some point kind of over here. And we'll do our x-axis, our y-axis, and our z-axis, but this is point A, not where they drew it in their picture. Now we have to try and figure out, I guess I need all these variables values for A, B, C, D, and F. Let's get those. Where did they go? Here they are. Oh, I want them up here though. Oh, for some reason that won't overlap. All right, well, we'll put them over here. There it goes. Just have to overlap from the right direction, I guess. All right, so let's work on AD. That one looks to be the simplest because it's actually in the the YZ plane. So I need to, from point A, I need to go up, that distance. I need to go, that's D minus F. So D minus F is going to be 2 meters. So that's 2. And then you need to go back this direction, A, which is 5. So I don't know how much of this I want to draw, but I'm going to go backwards 5 from point A. 1, 2, 3, 4, 5. I'm going to go up 2. And that is the end point for AD. So that'll be, we'll just call it AD. And its coordinates are x is 0, y is -5, and z is 2. Okay, so that's probably the most straightforward one. Let's get these off of here. Let's do AC. So again, it's going to start at point A, and it is going to have to drop down F, which is 2 meters, and also go back 5. So it's going to go back the same, and over C, which is 5 meters. So it's going to go back 5, back towards the opposite X direction 5, 1, 2, 3, 4, 5, and then it actually does not go up from A, it goes down from A a distance of F, 2. So this one, to draw it, I draw from here to here. So it looks like, it's on the z-axis, right? But it's not at all. Its x-coordinate is x of -5, y was -5, and z was -2. But when you draw it, it looks like it's going straight up the z-axis. So that's one of the difficulties of drawing these forces in 3 dimensions, but on a 2-dimensional thing. All right, so I'm just going to check and make sure I did that right. -5 for x, -5 for y, and -2 for z. Yep. All right, now we've got the last one, AB. For the x direction, it comes out a distance of B, which is 1 meter. So it comes out 1 for x. In the y direction, it's also going back A equals 5. 1, 2, 3, 4, 5. And then it's down below the point A by a distance of F, which is 2. And it's going to look something like that. So I'm going to draw from A to this point, which is this guy. And it looks like it's, perpendicular to the Z. Well, not Z, to the force AC. I guess this was AC. I didn't label it. But it has a x coordinate of 1, a y-coordinate of, what was its y? -5, they're all -5, and a z-coordinate of -2. So it can get really, difficult to draw these things. Now the picture here is actually reasonably easy to interpret because it's not set in an isometric orientation. It's, if you see these lines for y, that's not parallel to the isometric y. So it actually is twisted a little bit in the way it's presented, which helps out this particular drawing. All right. So assuming that we can get to this point, just interpreting the drawing, whatever it is, or the real live world situation, whatever it is you're working with, and getting to the point that you have the XYZ coordinates of the vectors. Oh, we left off F, didn't we? F, from point A, F does go directly straight down, and let's see, 1,125 newtons. So 1125 newtons. All right. So our goal is to find the forces in each of these cables, well, this cable and these two struts. I'm just checking it again to make sure that things make sense, and I think they do. All right. So what we do next is, it has another warning that we're not getting enough data. I think it's still okay though. All right. What we need to do now is the same type of thing that we did here, where we come up with x, y, and then now z equations in order to calculate the values for what I call them, AC, AB, and AD. Is that what they ended up being? Yes. Oh, I didn't label this one. This one is AB. Okay. So it may seem odd, but the first thing we're actually going to do is we're going to calculate the lengths of each of these vectors, AD, AC, and AB. And that's simple enough to it's just finding their, the summation of the squares and take the square root of that for each one of these. So it's like a squared plus b squared equals c squared, except it's, there's a third component in there. X squared plus y squared plus z squared equals the length of the line. So I'm going to do that in Mathcad just so that we have the whole thing put in there. It's a little bit cumbersome in Mathcad just because there are so many of them, but we'll still do it. And we're going to do x1 to mean, let's go ahead and number these so that we know which one is 1 and 2 and 3. AD will be 1, AC will be 2, and AB will be 3. So x1 refers to this 0 right there. All right. So probably x1 equals 0. I'm probably going to move this over, I think, so that I can look at it and type these in for you. x1 equals 0. These are actually dimensions, so inches, or actually they're meters is what they're shown in the problem. I don't know that it's going to be important to put meters in here, so I'm going to leave that off. Normally I tell you to put units on everything, but just to kind of speed things up, I'm going to not put them on these units. But these are all meters. Y was -5. Z1 is 2. And then x2, so this refers to AC, the one that looked like it was going straight up the z-axis. X of -5, y2 of -5, and z2 of 2. And then x3 was the last one that we did. Whoops, wrong thing. It had an x coordinate of +1. y2 of -5, and then, or y3, that should be a 3. z3, go over there, of, it ended up -2. And that z2 over here should also be negative. All right, those are our coordinates. To get the length, so L1, the length of cable 1, is going to equal the square root of x1 squared plus y1 squared plus z1 squared. And again, that would be in meters. And then we need an L2, which is the same thing, but with all the 2 numbers in there. And then we need a 3 with all 3 numbers. So we're doing this because the way we're going to write our equations, so there's our different links. So let's go back temporarily to here. So find my cursor. Here we go. Something like that. So here, when we wrote this equation, we did the x components, all the forces. We need to do the same type of thing. But here, cosine of 19 degrees, we did that to get this this component right here. You know, that's the TC x component. And what it's doing is, remember, the definition of a cosine is the adjacent side of an angle, and then you divide that adjacent side, divide the hypotenuse, and that is the cosine of that angle. This xy 2D thing, you know, all the forces are in the xy plane. Here, you know, we do have this one force AD that's in a plane, a coordinate plane, the YZ plane, but these other 2 are not, and AD doesn't have to be, it just is for this problem. So what we're going to do is we're going to do the same idea, but when, and this is going to be tough to visualize, but when I do the, let me erase some of these blue lines here, kind of get them out of the way. When I do the x component of AD, I want this angle. Remember, AD is not in the XZ plane. It's actually in the YZ plane. So this angle creates a whole new plane. And what I want is I want this AD projected onto the x-axis like this. I don't know what this angle is. I'll label it alpha. I don't know what angle alpha is, but this plane is kind of tilted, you know, to the left, I guess you might call it. I can't tell if it's actually streaming anything. It says it is, and it says there are viewers, but it doesn't give me a preview of if anything's actually there or not. So, can anybody tell in the chat if there is actually anything streaming? So I don't think anything's actually streaming. But I don't know.